好，就跟刚才我讲的，我就尽量用英文来讲，有些什么问题，如果你们听不懂，我用中文问问题也没有问题。另外这个 topic 呢，主要讲 non-logic devices in CMOS logic process，主要就是 for semiconductor. Actually, this all mean devices is CMOS device and logic process is logic CMOS process. So basically, the idea is based on my recent book，我跟一个 Cornell 的一个 Edwin Kahn 教授一块写的，这个 book 呢就是 name 就是 non-logic device in logic processes， 主要是 teach you how to design novel devices using logic CMOS process without process modification。这个 target audience 呢主要是 for useful fabless IC companies for best utilize the standard offerings from foundries for low-cost ICs and also faster to market. 因为这个一般 smaller 或者 medium-sized company， 你很难去talk to foundry to modify the process for you. If you do, it have to cost a lot of money and take a long time to process. So the idea is talk is how to best utilize the existing foundry process and to do modification from the design point of view or from a layout and design to go beyond what they're offering in the logic CMOS process in order to achieve low cost IC and faster to market. 我自己呢，你们有好多人可能已经大概介绍一下吧。我是78年进的科大，然后呢82年通过 CUSPEA 呢到了 University of Washington， 在 Seattle 的 University of Washington 拿的，然后87年拿的 PhD late 1987， 所以我的 career 基本上是2个半 career 吧。头一个about 15 years 主要是 physics research， 包括在 UW 还有 Brown Labs and Brookhaven National Labs， 主要是 did some research on superconductivities including high temperature superconductors， 然后一个 main focus 是 X-ray physics including X-ray absorption and emission spectroscopy， 包括 including the actually one of the things my proud achievement is actually we found the momentum conservation law in X-ray emission process。当时这个好像大家还没有 realize there's a found momentum conservation law there。另外也做了一些quasi-crystal or surface and semiconductor physics research. So in about 1995. 我就是因为在 Bell Labs 做了很多 surface 和 semiconductor physics， 所以就当时想去做一些更 device 更 practical 的东西，就 move to a semiconductor R&D， 就在 Sharp Labs America 开始做一些 CMOS device research， 包括 high K gate dielectrics and metal gate CMOS。 中间我们做了一些比较早的，实际是 earliest high K gate dielectrics work. I think actually my patent is probably earlier than Glenn Wilkes' patent from high K gate dielectrics. 这些 high K gate dielectric patents 我们有几个 patent 都被 cited 200-300 times from other patents。然后呢，因为做 gate dielectrics， 自然就做了 involve 一些 non-volatile flash memory 方面的 work。后来就 move 到 lattice 做了1年，FPGA 啊，还有这个 non-volatile memory related work。然后大概2001年左右，我就 move back to Seattle， work for a company called Impinj， working on radio frequency identification chips。which mainly focus on basically low power circuits and devices. So this is my kind of second career, semiconductor R&D. So about 5 years ago, I moved to a company called Intellectual Ventures, which mainly we do inventions and also invention management. They either invent ourselves or work with universities and individual external inventors to invent for kind of the future. So I'm mostly working on the IC related fields, 包括 semiconductor memories and FPGAs. And also later on, we actually moved to work, especially recently, we actually work on a lot of area on materials and food science. One of our main partners is actually Pepsi. So we actually did a lot of work with Pepsi on inventing new food processing techniques or new type of snacks and things like that. So that's kind of the the last 5 years. Actually, because I had some invention in semiconductors, I actually founded a company with a friend. He's managing it in China on kind of a non-volatile SRAM product. So they just started about a year ago. So I got about 37 US patents and also about 80 publications, including physics and semiconductor publications. So here's actually my start of the main part of my talk. I try not to be technical, but anticipating some, like Win and so on, probably not very familiar with the semiconductor industry. So probably 2 parts of my talk is pretty much non-technical, more dealing with the semiconductor industry overview and the economics of semiconductors. Only the kind of last section, the last half of third of the talk is a little bit on device and technical side. So on this section, I mainly do an overview of semiconductor industry, including Moore's law and the kind of the eventual stopping of Moore's law and what's our strategy for dealing with it. Then I'll review basically CMOS device and process and talk about economics and some of the best practice that were proposed to approach to the slowdown of the Moore's law. And then lastly, some examples of how to implement some of the ideas, including designing of non-logic device using logic processes. So I think everybody here probably come from the CUSPEA program, so all physicists by training, I guess. This is my kind of physicist view of a semiconductor industry. It's more of an inverse pyramid. Basically, the thing is, our physics point of view, everything is dependent on physics, and that's our contribution to the world. So starting with kind of quantum physics, including actual electrostatics, and you can build devices using materials. In fact, all the semiconductor industry is probably built with a handful of materials, including roughly around 10, primarily silicon oxide. Then you have the conductors like a tungsten, aluminum, copper. And sometimes you also have other type of semiconductor like gallium arsenide for power amplifiers and so on. But altogether, there may be around 10 type of materials. Although I think Zhenquan probably knows better, in semiconductor processing, you actually use a lot of other materials, but those all end up mostly not in the end product. It's used in processing, like all kind of acids and gas for etching and so on. But that's the real product end up in the device is probably around 10-ish. Well, actually, silicon CMOS is probably less than, it's probably around 5-ish. And then based on the 10 type of materials, you can build around about devices, semiconductor devices, mostly like MOSFETs and bipolar junction transistors and diodes and so on. And there are probably less than 100 type of devices that's been used in the semiconductor industry in a large scale. When we're talking about in use, it's probably used in roughly account for 95% of the IC industry. So with those devices, you can build all kinds of circuits to use, including SRAMs and DRAMs and different logic gates and flip-flops and so on. That may be out of around 1,000 type of circuits that you can build with these devices. In fact, for CMOS, the whole device, you might have only 4, 5, or 10 type of devices, but other specialty semiconductor use more. So with these circuits, then you can build the systems and architectures. This by architecture, I mean devices such like FPGAs, microprocessor, flash memories, and amplifiers, power amplifiers, so on. So all the basically ICs and chips. So those chips account for roughly 350, or maybe actually probably close to $400 billion of semiconductor market nowadays. With the chips, then you can build application systems like PCs and cell phones and switches, medical electronics, and solid-state drive. This is roughly a $2 trillion global electronics market. And then, of course, with those systems, then you can build application, software application, and that's probably tens of trillions in total economy market and millions of applications like a Facebook or Google's and so on. So basically, this is the inverse pyramid with the semiconductor materials and devices. It's basically a handful to making all kinds of applications in this inverse pyramid. Now, semiconductor industry, as everyone knows, is governed by pretty much the Moore's law, which basically says the number of transistors on an integrated circuit chip doubles every around 18 months to 24 months time frame. And this law has been proven and being extended for over about 52 years now since it's proposing. So starting from around 1970-ish, with about 1,000 transistors on a chip, now it's roughly about 20 trillion billion devices, transistor on a chip nowadays. In fact, I think the NAND flash chips probably are more. I mean, you can have a 512 gigabit of chip now, and even with the triple level cells, you still have probably 100 billion chips on a billion transistor on a single state-of-art NAND flash chips. So the Moore's law actually is, in its core, is actually an economic principle. Basically, it says since the cost of processing each chip stays roughly as constant, maybe around $10 to $100 over the years, the transistor cost per transistor is really going down every year because of the shrink and because of doubling of the transistors. So basically nowadays, the per transistor cost is essentially negligible. It's probably less than 1 millionth of a US cent on that order. So that's basically that's kind of the economic principle. That's what's driving the success of the semiconductor industry, is that with the small transistor, low cost transistors, you're able to adding the cost per function is much less, getting less and less each year, and the performance of transistors is getting better as well. So you can enable more application with the same or low cost, and that can basically propagate and you enlarge the applicable market that can be addressed by the semiconductor industries. And this will lead to more sales and making more money, more profit, and more money to fund R&D to continue the scaling trend. So this is basically the virtuous cycle that has been basically account for the success of the semiconductor industry over the last 50 years or so. But it's actually more of economic principle than physical principle, in the sense that all exponential growth will stop. No exponential growth can last forever. So basically, everybody agrees that Moore's law has been slowing and will stop eventually. And this picture is just showing the time and the technology node that basically measures the size of transistors, how it's scaling, and you can see roughly there is a slope change around 2009, 2010 range. It's indicating the slowdown of the Moore's law. And so, in fact, some aspect of scaling has stopped already. In this picture, it's basically showing on the top curve is the number of transistors as a function of time. You can see that's still continuing scaling in terms of number of transistors per chip. That's still scaling according to Moore's law. But on the same curve, you can see some other scaling has actually plateaued or more or less stopped already. One of the main thing is this frequency per megahertz in terms of the frequency. This is kind of the top performing microprocessor speed. It has slowed down since about 2005 also. Before when you buy a Intel, you buy a PC, you already see, oh, what clock frequency is this processor is running at. I think starting about 2005, you start not asking that question anymore because we cannot really scaling the frequency of the processor anymore. And mainly because it's a power consumption issue. The power consumption is proportional to the frequency of the processor, clock frequency of the processor. Because it's engineering challenge and the cost for cooling the chip, and that's more or less practical, because of practical limit, it stops the scaling up of the frequency of the microprocessors. And that's related to the power of the processor as well. That stops around 100 watt or so. So basically imagine a centimeter square silicon chip that consume about 100 watts power. So you can see how hard it's gonna get. Because the 100 watt light bulb, right? You can see the old incandescent light bulbs cost about 100 watts. It's really hot. That surface area is probably 10 centimeters per square. So this is really getting a tough problem. That's pretty much stopped the scaling of the clock frequency of the process. In its place, people are putting more and more cores on the processor. This one showing Intel has a 48 core, each running at probably 1.5 gigahertz rather than 4 or 5 gigahertz that they can achieve. So that's a way to people are solving the some aspect of the scaling problem. Another aspect for more or less make it harder to scale is the cost. It's been in economics. The cost of pretty much doing everything in a more advanced process is skyrocketing. Mainly because, for example, on the top left curve is the cost of building a fab in the most advanced process, which basically is saying the building a new 10 nanometer fab is cost more than $10 billion to build a fab. And same thing, to develop a 10 nanometer logic process is going to cost more than $2.5 billion to develop a process. And the last one is, given the process, if you design a chip in a 10 nanometer process, the overall cost of that, basically the non-recurring engineering charge cost, is going to be around $400 million. So basically, in the end, what you're saying is the scaling is pretty much at a stop for all the small to medium-sized companies. Only the big companies can afford, and the large IC companies can afford to move to the most advanced process. So that's, to practical purpose, all practical purpose, Moore's law, it's basically a stop for most people. So the question is then, what should we do? What to in the face of Moore's law stoppage or slowdown? To that, you can learn a lot from the history. This kind of a scaling, basically the history lesson from previous industry revolutions, like automobile scale, steel, or communications. They all had faced similar problem before, like communication, right? Telephone, people have a big rapid growth, and eventually everybody have the phone, and they stopped. So what have people done with that? And there are two main approaches. One is mainly from a design architecture point of view, with more innovation in that regard for dealing with the stoppage of Moore's law. This including, and people are doing now already, including more heterogeneous computing. That means instead of general purpose CPU to do computing, we actually use a special design accelerator for dealing special functions like vision and so on. This might be helped with like neuromorphic computing, try to learn what we can do from a brain, which is a very efficient computing engine, to see how it can help to using architecture point of view to improve and still continue scaling in an economic sense rather than um, more what I'm saying is more of a hard and a transistor number count and clock frequency sense. And of course, that's a big news last few days is about quantum computing, especially some announcement from 中国科学院和科大 doing some new quantum computing using photons. This is actually big activity also in the US and around the world as well, including Google and Microsoft, and they all actually invest heavily in quantum computing. So within the next few years, we actually might see a pretty significant quantum computing effort maybe being commercialized. Now, another approach we can do to dealing with the Moore's law, which basically is saying we try to make the chip and cost and cheaper, cost cheaper and cheaper. It's basically more use of more mature processes, but using innovation, try to drive the efficiency to it and drive down the cost further. And this is kind of the topic of this talk, and as well as the motivation for the book. The use of more and more mature process is actually has been going on for a while. More or less, you can see in this picture. This is a picture showing the number of wafers, the TSMC's revenue that come from the most advanced processes. You can see that in 2008ish, you can see as you roll out a new generation of advanced processes, there are more and more people. You start initially around 62%, and then you can up and up the peak around the 72%. It's still going up, but then as time along, more and more generation, and you can see that the number of processes, wafers running at the most advanced processors is actually going down. This means actually more wafers or more wafer start at TSMC is getting more and more contribution from the more mature process as opposed to the most advanced process. This is because the previous picture I showed where it's cost around $500 million to design a chip in the most advanced process, and not too many IC companies can do it. So naturally, you're forced to do more and more with the old and mature process. So this kind of more or less leading to the talk what I'm talking about. But before doing that, I'll review some of the economics and some of the basics of the CMOS device and processes, and before giving some examples in the last section. As you all know, semiconductor industry is tremendously versatile. They have all kinds of products, but actually all the products can roughly group into three main categories. You have basically the logic chip, which is being typically it's exemplified by like microprocessors or FPGAs or ASICs. Those are doing more logic functions. And then you have another big segment, it's called the MOS memory. It's basically semiconductor memory, such as DRAMs and flash memories. Those account for about another third of the semiconductor market. I think DRAM is probably around $56 billion revenue per year, and NAND flash memory is probably $40 billion. revenue per year, and other varieties is maybe 4 or 5 billion. And then another big segment is analog memory, analog and RF circuit. And with all these different products, they actually processed with special CMOS processes. And this starting with what they call the basic CMOS process, such as this process without you can basically making CMOS devices, and mostly which I mean by NMOS and PMOS, and without you can make logic ICs, SRAM and DRAMs. Now, if you add more features such as with kind of going into mixed signal and RF processes, you have to do that by adding some special devices such as MIM caps, basically it's metal insulated metal capacitors, or some high value resistors and so on. And with that, you can make analog and RF ICs. And similarly, by adding like DRAM capacitors, you end up with a very special process for making DRAM. So a DRAM process, making the DRAM ICs, and similarly for flash process, and mainly using flash floating gate transistor or charge trap transistors, you can make flash memory. So basically, this is a versatile process, to make all these semiconductor ICs. And then the key realization is this: with more of the specialized process, the wafer cost actually will generally goes up because of the process complexity. And that's typically the CMOS process. The basic logic CMOS process is the lowest cost process offered by a foundry. Now, a basic logic CMOS process, which offered by foundry, essentially they offer 4 types of CMOS device or transistors. Those mainly is basically logic. It's core NFET or core PFET, or then you also IO NFET and IO PFET. This process generally made on the same, this FET generally made the same process on the same wafers. So basically that's the basic devices offered from a foundry for a fabless customer to use in their basic logic CMOS process, which typically is a low cost process as well. This is another picture to illustrate the same point, is that you have all kinds of devices, as I shown before in the devices, but for typical foundries, they typically offer only 4 types of devices. For a couple of core devices with a generic VT, threshold voltage, and also IO device, either 1.8 volt IO device or 2.5 volt IO device or 3.3 volt devices. Of course, they give you options to have more other devices, such as low VT device, or low power process with high VT, low power process with medium VT, or low power process with ultra low VT, or high performance devices. But the question, the realization is this: with these options, they actually all cost more. In fact, it's probably cost a lot more sometimes, because some of the process might be more specialized and less demand and less competition, and it cost more. The most fun economic process are the generic process of the foundry. And all the foundries are trying to be competitive with each other because it's more easily portable from each other. And that's a competitive factor also makes generally the baseline CMOS process much lower cost than the process with the special options added to it. So that's the basic process. Now, in terms of IC, the cost of a semiconductor chip is basically on a per chip level. Per unit chip is basically the total amount of the money you spend developing the chip is called the total NRE cost, divided by, amortized by total number of chips that you expect to sell. So if you expect to sell 1 billion chips and you spend $500 billion development, then right away each chip will cost at least $2, right? Well, no, actually, it costs at least a quarter already. And then if you, with this non-recurring fixed cost, you have to add the wafer fabrication cost. This is basically divided by wafer fabrication per wafer, cost per wafer, by the number of dies that you can, good dies you can get per wafers. And then with that, you add the test cost per chip, and you also add the package cost per chip. That's your total net cost per chip. And so to kind of explain each detail a little bit more, so the total non-recurring engineering cost, the total fixed cost for developing a chip is basically roughly the cost of developing a chip design, including engineering cost and tooling, including the CAD cost, and the cost of actually set up the manufacturing tooling, including manufacturing tooling, the mask set cost, which can be tremendous when you for a more advanced process. And similar with the test costs, such as test setup and packaging assembly. Now, with the next page is on the wafer fabrication cost. Wafer fabrication cost is generally a function of a test process node, and in more fine detail is the number of how many masks you use for given process node. So for the given process node, it pays to minimize the number of masks you use. That's kind of the optional device that you need. And lastly, the wafer yield is a big factor as well, especially if your chip is very big. And the wafer yield is basically a function of size of the die and the number of masking steps. A typical function is a yield formula is given by this Bose-Einstein model for yield, which is basically saying the yield is a function of both the number of critical masks as well as the defect density of a given process, and well as the area of the chip. The A is the area of the chip. So sum all this together, and actually, I mean, before doing that, I also mentioned that because of this, the Moore's law actually, and same thing from other economics that talk about, that you can actually derive a corollary of Moore's law, which means, first of all, the one I mentioned before is that a transistor per transistor cost essentially zero in the recently advanced processors. So basically, the incremental cost of manufacturing a transistor is essentially zero. So anytime you can solve a problem with a design with throwing more transistor at it, that's probably your best bet to do. But sometimes you cannot do it. I mean, sometimes you cannot do. For example, if you want the non-volatile memory function in your chip, you probably are forced to adding a different process as well. So you might have to look into that. But in the case you can do it, you can always design around using transistors. And this is actually the one of the main motivation for the talk as well. So the second corollary is that economic scales so favors most basic process. This one is actually mentioned before. The most basic CMOS process is because of computation, because of the number of users, and because of the more wafer, more people using it, and the more learning that you can do. So it's basically a more generally the most lowest cost process you use, and generally offer a high yield as well because of the number of people, number of wafers that run in this process. And then the other one is kind of obvious that the process complexity, you want to favor simplicity, right? So that guarantees a lower yield. and you also does not want to modify the process because the foundries does not really generally support it, or anytime you modify a process, you incur development cost as well as the yield hit. And then lastly, you have to consider is the CMOS, um, the CMOS, the CMOS basically, well, one-time versus the recurring cost is that the CMOS process, it's you know, you have to kind of estimate how many chips and how many wafers you want to do in order to depend on whether you really want to spend time to develop a special process or make modification, or if you want just want to stick with the existing process. If you anticipate you're selling a lot of wafers, you probably pay for you to do process modification. If you do not anticipate a lot of wafers, you might try to design around it by adding more transistors as well. So this kind of summarize in kind of one sentence is more of a best practice recommendation for you're choosing a process or designer, starting with a designer chip. It's basically the focusing your IC development effort on using the simplest, most basic process with the highest volume processing, and try to avoid process errors and changes in order to save process time and to reduce the cost. So the last, well, I mean, that's kind of the example. I mean, we learned a lot of this mainly from our designing of a RFID chip from my previous job. And basically, the RFID, I think Xiaodong probably knows pretty well, is the RFID really value the cost because the tag chips are competing with the barcode. You're talking about pennies or sub-penny for barcode. So for RFID, you're talking about really you want to, RFID die has to be around pennies or less. So basically with that, what we learned from before is we try to use a mature process. For example, even though 99 nanometer or 65 nanometer process was available at that time, we stick around with 0.18 micron processes. And we use the basic CMOS process all we can, and actually try to design a non-flash memory, a non-volatile memory, and also some special function using the logic CMOS processes. Some other, actually availability. I mean, some other RFID vendors, including I think Quanglei in Shanghai, because they have special needs, they actually use SMIC's special E-square prime process, which incurred extra wafer cost, and that somehow you have to evaluate and judge depending on case by case basis. Just a quick comparison for RFID chip versus a state-of-art server chip. This is kind of almost two extremes of the IC industry in the IC industry now. For the RFID passive RFID reader, tag chip, it's roughly the one that recently rolled out by Impinj in Seattle, is what they call the Monza R6 chip. It has about 100K transistors. The size is about 0.46 by 4 millimeter square, so it's less than 0.2 millimeter square total size. And the process node they use is 0.152 process node, and the power consumption is about 5 microwatts. And the price they're selling is actually less than 1 cent. I don't know how much they're selling now, but I'm pretty sure it's less than a cent now. And they're expecting probably sell 10 billion or maybe 20 billion chips. On the other hand, you have this Intel's Xeon processor chips. It's a 72 core, 1.5 gigahertz chip. It's total about 8 billion transistors. And it's probably cost $6,000 each, and its power consumption probably around 100 watts. I don't know how much we're expecting to sell, probably 100K-ish for servers. and you probably can generate $6 billion market. But that's just too extreme. In this case, you use a state-of-art 14 nanometer process, while the RFID chips is using a 0.152 micron process. So that's kind of the basic introduction. Any questions? Okay, now that I just give some quick examples, they're more technical, just some quick examples of designing non-logic devices using kind of logic CMOS processes. The first example is basically designing a non-standard VT transistor, what I call the band gap transistor. So I think most of you know, a standard MOSFET is like this. So you have a substrate, you have a P well, then you have an N plus, for the NFET, you have N plus source and drain, and you have an N plus gate. So this one technically offers a foundry maybe with a threshold voltage of 0.3 volt. That's a standard foundry offering. Now the question is, what do you want to, what can you do if you want other transistor with other VTs? One option is to do is what we call the band gap engineering. This is shown with the bottom figure. This figure is basically you replace some of the a portion of the N plus gate with a P plus gate. By doing this, the whole transistor become NFET transistors with a threshold voltage that differ by a band gap from this standard NFET device. And this is basically end up with a FET of 1.4 volts. And you may ask, we do need to have this N plus region here, because if the P plus right button to the gate, then there might be a risk with the P plus implant into the source and drain that will basically short the P well. So that's not it'll make the device non-functional. And you can make this device, as I shown here in this layout, using a standard layout and standard CMOS process. And actually, this device is actually very useful. It's been used in the RFID chip in with a so-called band gap reference circuit. I won't go into detail later, but basically it's a mirror circuit where you have the output, the V out. We replace one of the N P MOS with a band gap P MOSFET, and as a result, the output voltage here is basically a band gap of the silicon. It's independent of the mismatch of the transistor and so on. And so this is a very low power, small area band gap devices, as opposed to traditional band gap device from using bipolar transistor and so on, which costs a lot of power. So this is very useful for RFID device. Another device is basically the high voltage transistor in CMOS. The standard NFET is basically a 3.3 volt. NFET can now go up very high in voltage. For example, an example of the 3.3 volt I/O transistor. Basically, you have several places where the device can break down, including the N plus to P well that breaks down around 7 to 8 volt, and then the gate to substrate breakdown around 10 volt. So you can now take this to any higher than with safety margin, more than like 5 voltage. But with a simple modification by, for example, inserting an N well in this region and move the N plus region away a little bit, you actually can make a so-called lightly doped drain MOSFET that can go up to 12 volt in this device. Actually, in my book, you talk about other options. You actually, more option, you can bring this device to up to 25 volt as well. So this is a way you can make a high voltage transistor with the standard logic process, where the foundry says don't take any transistor above 3.3, 5 volt. You can actually design device with a 12 volt or 15 or 25 volt even. And I should emphasize there are no extra mask or processing for this process. And the device is very useful. Here's an experimental curve. I won't show, talk too much, but it's very useful for high voltage switches, for maybe embedded flash memory on the logic processes. Can be used for charge pumps and used for display drivers. For example, if you make a simple display driver, instead of using a high voltage process from a special process foundry incurring additional cost, you actually can use LDMOS from a standard basic logic process. Another class of device is basically you making floating gate transistor in logic CMOS process. You probably most of you familiar with the flash memory, which is basically a double polysilicon process where there's basically source and drain, and then you have a floating gate that's sit below a control gate device. And the floating gate can store charge that basically store the information for the flash memory. So how do you make a similar floating gate device in logic process, which typically only have a single poly available? Because this double poly is very expensive. It have several additional processing steps, and now will have a much more costly than the logic process. A way to do it is basically using logic process is an example I shown here, is that you can use a two PFAT transistors to construct a floating gate transistor. In this example, we basically put two PFAT back, actually head to head, and use the N well of one of the PFAT as a control gate, and the other one basically source and drain as a sense transistor. And if you use this two PFAT as an I/O transistor with a 17 angstrom gate oxide, and the floating gate actually can hold the charge very well. It can hold the data retention definitely more than 10 years that you need to, and probably even more than 50 years if you don't too many programming erase cycles. And this type of device has been used in flash in RFID chips to store the code in the flash in the RFID chips pretty extensively. Here is example of a basic layout and some of the spec of this device that's made with the TSMC 0.18 micron process. So in the application of this non-volatile memory is actually pretty widespread. Actually, there are quite a few companies, generally they're small companies, all dedicated to building the embedded process using logic CMOS process. And because the application, as I mentioned, one of large classes RFID chips, other application is to use this to store the bits for trims, for analog ICs, and for chip IDs, and sometimes even for small microcontrollers to store code in it. And also it can use to store security keys for to keep your ICs safe. And in fact, sometimes it can store digital copyright management kind of information for storing in E-squares and other type of chips as well. So it's the application is quite a lot. So to summarize, actually, my talk basically the book is focused on planar process. We kind of wrote the book before the FinFET really took off. So because our IC is moving to 3Ds, and NAND flash, is already processed, has already moved to 3D as well. And logic is first moving to a 3D transistor like a FinFET. And also other process such as silicon through silicon vias and MEMS process also. And the process getting very complex. and there are actually more opportunities for innovation in that regard. And basically the key takeaway is, and you can always do more with the standard offering from the foundries. So you know, that's kind of the spirit of this talk, and that's of the book, that hopefully you can all, you know, use your imagination and use your design skills, try to look for opportunities in your own work in the future. So that's kind of the my talk. So I welcome any questions you have.
燕姐，我是郑权，有个问题啊。
郑权呀，
你这个书名叫 Non-Logic， 你能解释一下你刚才讲的与这个 Non-Logic 的
？Non-logic， 因为我们是用的比较 narrow definition， 这个 logic device， 实际是本来我这个书名啊比较长一些，后来他们那个 publisher 要想 narrow down， 我本来的 name 是 The Art of Non-Logic Design of Non-Logic CMOS Devices in Logic CMOS Process。So logic 我的意思就是说，本来是这个我这个 narrow 就是 logic CMOS process 嘛哈，那个 CMOS 那个 device 呢，就说它是一个 logic device， 我的 transistor 是一个 logic transistor。我这些比如说那些 flash 那些 floating gate memory 还有 LDMOS， 他们做的 function 都不是用来 design gate design， 不是用来做 logic gate， 所以是。我就说，我认为它是 non-logic device。对。
So very good name for the book.
Thank you. Yeah, it's a little bit too long. I mean, because I think a lot of you probably read The Art of Electronics. I really like that title. So initially, I named my book is The Art of a Non-Logic Device. But I think it's probably good to shorten it because I mean, it's not really, it'd be too big a name to call it art.
No, it's a good name. It's provocative because non-logic logic device.
Yeah.
Yeah, I'm curious, how do you hook up with the other professor to write the book together?
哦，我本来这个书啊，我已经写了很长时间了，所以我就找人这个 review。这个 professor 呢是怎么说？我就说我现在这个工作和特别是以前那个工作呢，我们跟好多的 university 教授有联系，希望跟他们一块合作 invent 这一些 new future 吧future for semiconductor future foundry。所以我就我忘了通过什么途径正好认识这个教授，我就说你要不到 summer 来，到我们公司来做一个 summer invention fellow。他就来了1个月吧。这个 Cornell 他也是华人，在台湾来的。他是那个他正好 summer 有几个月有几个星期没有事了就过来，所以我们就比较认识。我就跟他说，我最早的时候我跟他说我想写本书，要不要跟他写？但2年前他说不行，太忙了，他不帮写。后来我这个快写的我差不多了，我又找他看，我说我现在还在写的快差不多了，你要不要帮着我 review 一下？如果你要想合作也一块合作，因为我知道他有不少东西可以做出来。他就说那后来一看他那个 summer 正好他又有几个星期有空，他说那我正好又可以写上个2个contribute to chapter， 所以那个有2个 chapter， 一个 on CMOS sensor。还有一个那个 non-linear RF device 是他主笔的，他另外正好也帮我改了好多这个东西。我前面有些东西实际还不是很精确，他帮助有改了一下，就找到他了。
Good. Yeah， 因为上次看到那个张涛写的书也是一个 collaboration， 好像这个就有点像做 business，you need a partner，right？
对，你这个指导也写，当然有人帮忙，有人跟你这个跟你讨论是最好了嘛。因为就是说我当时写的时候，因为有好多东西你真正写的时候就发现有很多问题什么的，因为大家都很忙。我找的 review 的人呢，他们大部分也都是 cursory 帮你 review 一下看一下，你知道意思吗？ 你
Yeah,
找
not a deep.
co-author 的话，
Yeah,
你起码2个人 second set of eyes，make sure everything's right。as much as you can， 因为你自己做的话，你特别这种书你不太容易找到，而且比如说如果你在学校教书的，也容易找 graduate student 认真帮你看一看，怎么也行。我当时正好也没有，因为我这也是业余时间做的，我们公司这个也不是做这方面的，所以业余时间做也没有去找学生，也没有弄，所以基本上我自己就写，这找人做嘛，就是有些以前同事 review 一些，他们也不会花很多功夫 review。那正好这个 Edwin 呢，他是 very detail oriented， 所以我觉得我是 lucky 找到他帮助，还是改了一些地方，有些不太很精确，甚至有些地方可能有错误的地方，帮着改一改。
挺好。
谢谢。
严军啊，这是小东。非常好。
谢谢。
a couple of questions。第一个的话就是 floating gate， 这个实际上是原来的我 remember 是 Impinj 的它的key focus， 后来的话就把它 FID 的 tag 做它一个应用而已，后来的主页变成 FID。这个 fundamental 的 pattern 是你做的还是谁做的 ？Chris Diorio 还是谁的？
最早的应该是 Chris Diorio 吧，我们那个Impinj 这个公司放的时候，就是正好那个 Chris Diorio 跟那个 Carver Mead 他做 research 的时候就一直用 PFAT， 所以他就一直就做这个东西。但这个没有什么 fundamental pattern 呢，我意思就是说有些具体 design， 比如说我和他们有一个 pattern 是 differential cells， 但是我刚才呢讲那个有2个 PFAT 放在一块呢，那个东西肯定是一个 obvious general knowledge 大家都能用的。我们得到 pattern 呢就是得到一个 differential cell 的 pattern， 因为对这个是因为这个 PFAT 嘛，它有时候 reliability 还有一些问题 ，differential cell 正好这个 power 比较低，所以 RFID 还比较管用。但是呢，你如果要 density 比较 high
对，不好意思，这个 process 后来的话就是在台积电 TSMC 的这个是 exclusive for Impinj 是吧？
没有，现在就是说它这个所以我这个我这个 talk 就是说我们这些 process 就是用 standard logic process 都可以做的，就是说我们当时做的 TSMC 根本没有做任何 modification， 因为我们当时 Impinj 的小 startup company， 所以他不会给你做很多 process modification， 所以做的就完全是这个 standard process。即使现在我觉得这种 device 都可以在 SMIC 啊，在Global Foundry 应该都可以用。
对，这就是我的一直在疑惑，像坤瑞他们都是用 expensive EEPROM 的这个 process， 对这个对 tag 对 RFID 推广很不好的。
对，但是它 process 就是说，怎么说呢？就说这就有一个 trade off 的问题 ，right？ 他们 target 的就是说，也许本来他们没有 focus on 这个 low density 的。如果你这个 memory size， 这个 non-volatile memory size 超过一定的程度，比如说超过一个 K bit， 这样的话有可能这个用它的double EEPROM 可能就已经是 more favorable 了。因为我们这个时候我跟你说那2个 PFAT，right？ 你2个 PFAT 必须有2个 PUL， 这 PUL 是一个 big transistor， 所以我们这个 memory cell 呢 transistor 这个 memory cell size 是非常大的，相对来说可能我具体忘了多少了，反正几十个 micron square 吧。那你要用个 double E square prom， 他们一个 fat 一个那个 double E cell 可能一个 square micron 左右，所以这整个 transistor size 就非常大。如果你 density 很高的话，那肯定用 higher density 是比较划算的。所以他们坤瑞呢，现在就他们的一个 specialty， 我具体没有讲，我大概去年夏天跟那个闵浩聊过，他们就是还是主要想 focus 一些 higher density， 包括 那个像波音啊、Airbus 他们用的大概64 gigabit 的什么这种 chip， 对他们来说那 WE 就比较划算了。像用我这上面讲这种 memory logic process， 一般来说1K 最多2K 到2K 4K 就已经不是那么，已经不如那个用 WE process 更 competitive 了。
对，这坤瑞的话，它是基本上是 2K and up。
对。
就像电子车牌的话，它也是 2K 的这个 memory。
是吗？哦，中国这个 standard 标准是 2K 的。
哎，对，它现在就是它要用中国的叫国密算法 SM7。它是 2K 的。
对 2K 的可能是 borderline， 就看你这个 process 怎么样了。因为这个 transistor 这个 memory cell size 还是比较大。
另外一个related question 就是说这个 NXP 是做的最便宜的，现在的话 tag 的 IC cost 应该是0.6美分，比这个 Impinj 做的更小，这个 die size。他们是什么样的工艺啊？
我具体还真不太清楚。你说0.6它是卖的价钱还是它的
cost manufacturing
cost 啊？cost 我觉得倒不一定。我觉得Impinj现在他们的 cost 应该，我算了一下，这我没有，现在已经离开5年没有一分。他们要看他们的 die 和 wafer， 他们可能应该0.5美分左右。
OK。
就是说这个Philips NXP 呢，我还真不知道他们用的是什么 process。我知道以前 Alien 呢 ，Alien 用的也是 single poly 这种 E-square， 跟我们讲，我说这个一样的 process。Alien
是在 Tower 做的。
Alien 对 Alien 在 Tower 做，以前他们 Variety Logic 用他们的 memory 嘛哈，后来 Alien 一直在 Tower 嘛，没有转到别的地方。
对。
他们因为是用那种 Variety Logic 他们的 memory， 后来Variety Logic 跟 Synopsys 一块把 Synopsys 买去了 ，Variety Logic 把这个Impinj 的 IP 这个 non-volatile memory business 买去了，后来又被 Synopsys 买去了。
好的。
对，
谢谢啊。
谢谢。
我有个问题，你可不可以 go back to your slide 14？
14？
Yeah， 这个是科普了。
没问题。
Yeah， 这个你可以简单的介绍一下，这个是 MPU、MCU、DSP 我知道呀 ，ASIC 我也知道。
MPU 是 microprocess unit， 就像 Intel 的这个 processor 哈。
OK。
一般都称为 microprocess unit。MCU 是 microcontroller unit， 就说很多这种小，一般来说就像 SOC， 更类似于 SOC 的，包括一些很多的一些 control function 啊、I/O 啊这些东西都上，有些更多的是包括这 embedded flash， 就是 code 都在上面，包括比如说它是一个更 system 都在里头，它这个 code 啊什么都放在这个 chip 上面。MPU 呢一般是 higher performance， 就像那个 PC 啊，这上面的 processor， 它的 code 呢实际都存在那个 disk 啊或者 solid state drive， 然后用的时候它把它调到 DRAM 里或者 memory 里头。然后 MCU 呢一般是一个 system on chip， 它的 code 呢都已经 store 在比如说 chip 上，好多一些 control function 啊，有些比如 control on off switch 啊，这些 I/O 啊都在上面。像的 MPU 呢基本上是 fully processing based， 就是 cores。
OK， 那实际上就是 CPU， 你讲的就是基本上对 OK。
因为 CPU 嘛，总共大家都基本上说每个 processor unit 上面都有个 CPU，MCU 上也有个 CPU， 但 MCU 呢一般是比较功能稍微小一些，功能比较全一些，包括一个 CPU， 包括一个storage， 包括一些 cache， 包括一些 I/O function control 啊，有些直接你把一个 light 一个比如说 LED， 它直接 control LED， 或者就直接 control 这个door 的 switch 啊什么之类的哈。那 NPU 完全是一个 processor， 只是做 computation basically。OK，
那就是像什么 GPU、TPU 啊，最近什么
那个
Google
应该可能都算 special purpose logic 了。GPU 特别是 general purpose GPU 应该都算是可能那个 special purpose logic。
OK， 那也像这种小的这种camera， 那应该放在什么 category？
你说 camera 是具体什么样的方式？
like a cell phone camera 是吧？
它里面这个是一个semi IC 的嘛 ，IC 的 camera 呢上面肯定有一些CMOS， 实际 CMOS image sensor 应该没在里面，没在这个不算 semiconductor， 所以
I see，
这个 product 应该是IC 的 product， 我具体没看哈，我理解应该是这样，因为有些像 MEMS 啊什么都应该没算在里面。
MEMS 应该没算，但是像这种
CMOS image sensor 也应该没算在里头。
OK，
可能是在最下面嘛，other semiconductor。
那也有可能，对。
OK，
我弄这个图的，真对不起，还真是没看的，包括什么？哦，我回去看了它，但真还没解释，它可能 cite 另外一个 book 上。我如果看，对，我觉得算。我觉得350个 billion、360个 billion 可能那个 image sensor 倒是也不大，它可能1、2个 billion。
对，这个应该的话，你是全部包括 semiconductor 的 revenue 全部在里面了。
对，有可能。
400 billion， 所以说 CIS 应该是在下面other semiconductor 里面。
对，那有可能是。
OK， 也小东，因为你要下一次肯定要讲什么 Internet of a Thing， 对吧？假如你能够把这个 thing，you know what is that thing that
everything
I know
that's it，
包括的话 embedding in human body
I know but try to do a map from the thing to here, okay, so then we know what are we dealing with, okay. No, I mean
yeah, you probably should call it the Internet of Everything. That's what Cisco like to call, right?
Yeah.
So they, yeah, 小东的 thing actually means just a thing. It's very general. It's more 翻译的 thing. 我们那天好像有个讨论，这个 thing 它是这个翻译的 thing， 所有东西都可以 internet 起来。
Connecting everything.
Yeah. So if you can spell it out, it will at least people know what you're talking about. Then people can think of other things.
Yeah. Okay, all right.
但这个 thing 不包括这个不包括 soft things, papers.
Yeah, 就是 physical thing.
Yeah.
物联网。
对，是物联网。
物体。
还有一个就是你35 slide 35. Slide 35, you talk about security keys, right? So those can be dynamically stored, right?
Sometimes you can store you can basically like a password, right? You store and you need to store in a basically non-volatile memory. Yeah, exactly what you're saying. It's not those dynamic. 你知道有些的 security 它是那个通过时间变化的哈，我不是指那意思，我意思就是说，比如现在大家你到银行，美国这边真没有啊，中国有好多 USB key， 你拿去到银行，那你的 key 就 store 在那里头，哎。
Okay. Some are hard coded, some are just still can dynamically written or written, yeah.
对。
Okay.
有的 store hard code 的你，比如说我们说这个 memory， 有的时候你可以 design 成 one time read memory， 意思就是说你写一次，它就把 function disable， 你不能再写了，那就变成 hard code。另外更狭义的 hard code 的就是你做 wafer processor 的时候 ，processing wafer design 的时候，直接就把那个 bit 都给锁定了，这是两种不同的。
好，谢谢。
唐怡这边，我有个问题，那个你这里讲到一个用两个 PFAT 做成一个non-volatile memory， 这个是 new to me， 我也是应该是外行了，我已经学过这个课，那个DLSI， 但是很多年就是也没在这个领域里面。那么像看起来这个非常 interesting 啊，就是因为这样子的话，应该是它要比那个 flash memory 还要更快，
你最后一句没听见，你说比 flash memory 更快？
是不是像这样，就是用这样的方法做成了一个 non-volatile memory 的话，是比 flash memory 还要快一些嘛？
这个到这个快慢是完全看你 design 了哈。它这个我们这样 design， 比如说特别是我刚才跟小东讲，我们做differential cell 那种 design 会更快一些。它实际这个 flash memory 呢也有很快的 flash memory， 就看你怎么具体 design 呢？因为有些 NOR flash 实际是很快的，可以做 nanosecond read。我们一般说这个 NAND flash 很慢呢，是因为它是什么呢？它要 pack 这东西很 dense， 它就把很长一个 chain， 好多 transistor 跟串联起来了。你串联起来吧，你那个电阻就比较高，而且你每一个 transistor 都要 delay 一些，所以它速度就慢了一些。但是呢，它这个 density 就非常高，因为它我这个没讲，我另一个套上有，实际是最后我这最后几个 back up slide， 实际这可能就更麻烦给你。实际它是几个怎么回事呢？它是几个 transistor 啊，就比如这个 curve， 不是你们能看见吗？这是一个 3D 这个它每这个 fin 呢是一个 NAND storage transistor， 它可能把10几个连到一块儿了，呢，而且是中间呢，它这个你要读的时候呢，你要通过这几十个 transistor 都要通过的，那每一个都要慢起来，所以整体就慢了很多。它是因为这个 architecture 和这个 density requirement 让它慢了。你如果把一个完全这个 3D 这个就刚才就是在32页这个 transistor 也可以做的比较快，也可以做的很快的。如果一个 transistor 的话，也可以做的很快。所以这个 speed 的话是更一个 architecture 和一个 design 的问题。当然了 ，3D 我们这不是讲 3D 就另外一个问题了。3D 是什么呢？它这个 3D NAND flash 呢，它是怎么回事吧？它这个 channel region 呢，它是一个 polysilicon channel， 因为它不能做 single crystal， 因为它是一个 deposit。它这个 polycrystalline 的话，它 mobility 就很慢。所以这 3D flash 呢，它 intrinsically 是更慢。但如果一个 generic 这个 double poly transistor 的话，不一定比我们这个慢。
价格方面呢？
我们的好处呢，就是说呢，我们不需要 special process， 但是呢，这个 transistor memory cell 呢比较大，所以你如果比如说一个 chip 只需要比如说1个 K 的 bit 的话，那用我们这种 design methodology 呢可能会便宜一些。你如果需要比如4个 K bit 或者是1个 gigabit 的话，这用我们这个根本就 not practical， 因为你用2个 transistor 把它 fold together， 而且这个 N-well size 一般比较大，这个是不划算的。所以我给那些应用呢，一般都是这种比较小。你看这所有的应用呢，都是这些 small， 都是1 K bit 的或者 maximum 32 K bit 的这种 special 应用。
理解。谢谢。
燕云，我再问问题啊。因为我经常去台积是我们的客户啊。虽然大部分时间都是做这个 leading edge， 像现在是10 nanometer FinFET 在生产嘛。 但是我也注意到台积还有很多旧的厂子，像原来的8寸的厂，但是还是在开工，还有很多事情做。是不是因为有很多像你刚才讲的这种logic 还需要这种 fab 的 capacity？
有些 logic， 而且有很多还是特别 specialized 的，实际更多。像我知道他们8寸厂什么的，我们比如说我以前的我说我讲这个主要是这个我说那刚才那个公司叫 Impinj， 他们用的都是8寸厂的，都是最高用的0.18呢0.18 micron process。它8寸厂有好多 special process， 大家就说，比如说 display driver 哈，它需要 high voltage process， 这样的话。它就更 tougher to port to the more advanced process。而且比如说这种 embedded non-volatile memory 啊，一般更难 port。所以这个 logic process 是更 leading edge。当然这个 special NAND process also 也是 leading edge。但是那个你看你们的 more advanced process 的，一般它都没有这种 extra feature， 比如包括 embedded flash memory。包括比如说 CMOS image integration， 包括 high voltage display 这种 function 一般都没有，因为这东西不是 logic function， 这就刚才我讲的 logic transistor versus non-logic transistor。因为 display driver， 你如果你这 process 知道吗？哈，如果它比如说它这个 process 同时要做一个非常 fast 的 core device， 而且还要做一个能让比如说20 volt 的一个 high voltage process， 它就很难 integrate 这两个 together。因为你的 high voltage process 必须 anneal 时间很长嘛，哈 ，anneal 很长，你把别的 diffuse 就没法做很 compact，
对，
而且会产生 defect oxide damage something。所以呢，这个一般的 leading process 只是做 logic， 包括 Xilinx 啊 Altera 就 push for that。这个 extra device like high voltage device or embedded non-volatile， 一般都 lagging like 2 nodes behind or something。但是我中间前面有一个 figure 讲啊，你们因为是你们 sell 这个 equipment 主要 sell to leading edge， 他们实际是即使 TSMC 的话，他们那个 big business 也是本来是就我是这个哪个 figure 是那个这个 figure 我也是前几天为了准备这个 talk 刚找到，就是说以前我也是看 TSMC report， 他们基本上就是说所有东西就是强调啊，我这个28 nanometer 我现在已经 50% of the revenue 了 whatever。你现在看就是整个作为 migration 这个 more and more leading process become 这个 less and less overall revenue。
是
啊，因为就是大部分的 customer cannot afford to move to that model， 而且也不需要了。
很多还在用 TSMC 的28 nanometer， 其实那时候在2011年就已经成熟了，但是现在
对，我跟你讲嘛，我们还用0.18的，那是2002年是这么说的。
因为我们现在开始做5个 nanometer 的研发，我们的设备要测量5个 nanometer 那种制程的 control 啊。
Yeah。Well, there's still big business there， 因为这个 Intel 啊，这个 Samsung、Apple 啊，还是想去做 ，right？
是。
以后这个 Google 啊，这个 Microsoft 都想做 AI 啊，都想 neuromorphic computing 这些东西 ，GPU 也都需要，所以还是有 big business。
我今天也是开眼了，没有想到这么多device 还需要这个 foundry 来生产。
啊，那肯定是这是很，他们那个 A inch 基本上都没有 close 嘛，而且 A inch 这些 N inch fab 一般都是 very full， 因为有新的 generation 用出来，他们这个老的产品既然弄就不往新的 port 了，如果他们产品比较 mature 的话，就不往那边 port， 因为他们老的 fab 他们已经 fully depreciated，
对，
所以你产生的就是基本上是净利润了，除了 operating cost，right， 基本上就净利润了。
对，而且这个制程都很成熟，良率很高。
对。 而且经常是都 fab 都是 full 的。
这样。
现在实际上是一个8 inch 的 Renaissance， 现在8 inch 非常 tight，
是吧？
非常 tight， 那个每个8 inch fab 都很满。讲 Jazz 的，它是140% full。
啊。
主要是物量
140%，我知道110%，140%是打不到。对 ，Renaissance 这个 microcontroller 做的很好哈。那个小东，你们公司在什么地方？
在上海啊，嘉定啊。
在嘉定啊，现在多少人呢？
几十个人吧。
啊，不错，行，下次一定去拜访拜访。
好的，好的，欢迎欢迎。
那个郑权，你还得经常去TSMC，经常 travel 哈。
每个月都去。
啊。什么时候到 Portland 呢？
下次吧，下次。
Okay, let me know. We probably meet somewhere in the middle or something.
可以，我可以来拜访你，因为我去 Intel Portland 的，也蛮多的，
对。对。
好，下次拜访你。
Yeah， 没事 ，Let me know。我下次去，我估计说不定5月份会去 Silicon Valley 一趟。
那
已经5月份了，不一定了。原来说5月份可能。
没关系，你来了，反正。
I'll let you know。
通报一下，我们可以聚一聚。好多年。
你们谁要到西雅图转机或者什么都告我一声哈，我们聚一聚。
好的
，OK。我那个
问。
好，谢谢。那个不是是几月份啊？什么复旦的校长去湾区啊？你会去吗
？5月20号，我有计划去。对。
那我再看一看时间，我现在还没有。
要不把你加到湾区那个群里面吧？你不在吧？
我记得
你可以让老谭
讲过这个事儿，对，但我
让老谭把他加上去。
我发现这个微信啊，就有点不好是什么呢？你这过几天不看，夸以前多少东西都过去，根本没办法那什么。我觉得这微信这个问题是必须得解决。